Hello everybody, this is Avantik here. Today we'll be discussing about naive Bayes. The agenda will be as follows. The first part will be introduction of Bayesian theorem, little fundamental around it. Naive Bayes classifier, Gaussian naive Bayes, multinomial naive Bayes, Burnolis naive Bayes. Then we'll be getting into naive Bayes for out of code training. Okay. Let's first understand what's naive Bayes doing here. The first thing to get into is it's based on Bayesian theorem. I'll not be getting much into it, but still some foundational knowledge about it, and it's very much suited for high dimensional data. It is simple and outperforms many of the sophisticated methods. Rather than attempting to calculate the probability of D1, D2, D3 for a given hypothesis. Say you have three columns, G1, G2, and D3, and this is the hypothesis. Okay, so rather than calculating what is the probability of this particular value which is there, what's the probability of this particular value belonging to this class, right? Where you have to take the relationship between the data also into consideration. You're simplifying it. That's why it is called naive Bayes, right? You're simplifying it. You're telling that you assume that these features are independent of each other. So this is equivalent to probability of D1H into probability of D2H into probability of D3H, right? This is the fundamental things around it. Okay, let's understand few more terminology that is required to get through this entire thing. One is class probability. Okay, class probability is for in fact by class classification. So you have two classes, class 1 and class 2. So class probability is count of class 1 divided by total occurrence of class 1 plus class 2. That is your class probability of class 1. Then the other thing is class probability of class 2, which is count of class 2 divided by count of class 1 plus count of class 2. Okay. The next thing is understanding conditional probability. Okay. So let's take a data set which is something like this. We have weather and we have sports. Okay, so weather is your sunny or rainy. And the value are chess and tennis, right? These are the possible classes. So what is our conditional probability? When target is tennis, we want to find what is the probability of weather being sunny, right? This is what is. So what we are doing here is counting the number of events for which weather is sunny and target is tennis divided by total number of events where target is tennis. This is giving us this probability, right? What is the probability of weather being sunny when the target is tennis? This is what is conditional probability. We'll use this in our naive Bayes classifier. Okay, so let's see now. Let's start with an assumption. Say, okay, for the same data set, we want to predict what is the probability of a person playing tennis if the weather is sunny. So what is the data set? Okay, and what will that person do if the weather is sunny? Will he play tennis or chess? That's what we want to figure out. So for that, we have to figure out the probability of each of the events, probability of that person playing tennis versus probability of that person playing chess. Whichever probability is higher, that will be our final verdict. So let's get into this case where weather is equal to sunny, right? This is our data set. Okay, so let's first calculate for tennis. So what is the probability of whether it's sunny and the person playing tennis, but the possibility of it is this as per naive Bayes, right? This is the particular condition probability and this is the total class probability, right? This is the possibility of tennis. Then this is the possibility of chess. Of course, this this will not be in the scale of 0 to 1. Okay, so you have to convert this or normalize this. So what we can do, possibility of tennis divided by possibility of tennis plus possibility of chess. That will be probability of that person playing tennis when weather is sunny. Okay, the other thing is probability of that person playing chess would be possibility of chess divided by possibility of tennis plus possibility of chess. Okay, so whichever is higher, that will be our final verdict. That is what this is saying here. Okay, this is our naive Bayes classifier. Okay, of course, this is only one feature here, right? Weather was only one feature. So in case you are adding one more feature, say skill. and we have three categorical values, low, medium, high, and you want to take that into consideration, you simply add this as a conditional probability. This is what it is. So probability of skill, if the data set has weather sunny, and skill moderate, right? What is the probability of he playing tennis or versus he playing chess, right? So this is how you calculate. The possibility would be this value into this value into this value. This is the class probability, this is the conditional probability. This is with the probability for tennis. You will similarly calculate probability for chess, then you will normalize it, right? Then based on whichever is higher value, you will conclude that. So this is how naive works for categorical data. But so all we have seen so far is naive working for categorical data. How does it deal with continuous data? Okay, because sometimes your features will contain continuous data. Okay, for example, the example that we'll be taking iris data. Iris has 4 columns: petal length, sepal length, petal width, sepal width. 4 columns, right? Okay, so and all of them are continuous. We want to find which class does the data belong to, whether it's Sentosa, versicolor, or virginica. Which class of iris does it belong to? We want to do that. Okay, but one fundamental assumption is before you apply Gaussian naive Bayes is that the columns should exhibit normal distribution. If it is not the case, you want to use any of the transformation technique to convert your data into normal distribution. Okay, and if the data exhibits normal distribution, this is the probability distribution function of it. So given, say this, if the data distributes normal distribution, right? So given a particular, and given a value of mu, the mean of the data, the standard deviation of the data, and value of x, you should be able to predict the probability, right? Using this equation. So assume that we have continuous column in the previous example, like precipitation and windy. Okay, so what you're doing here, you're calculating PDF of precipitation. There is probability of this thing, and and when the class is tennis, you're calculating probability of precipitation. When the class is, the target is tennis, you're calculating the probability of winding. Okay, this is a conditional probability, or multiplying that with the class probability, which will give you probability or the possibility of tennis. Similarly, you'll calculate the possibility of chess, and then you'll normalize them, and whichever is final verdict will be your final outcome. Okay, so let's do that on iris data. So from the data, we are creating a data frame, and we are creating a model here, Gaussian naive Bayes, and we all know that in iris data set, all the 3 classes are evenly distributed. So there is no problem with imbalanced data set and all. So you don't have to configure anything explicitly. And here it is, you're training the model, you're predicting the score. Of course, you're predicting the score using the same data which trained the model. So it might not be the best way, just to show it here. So that's how Gaussian naive Bayes is there, and it works on continuous data. Okay, now let's get into the multinomial naive Bayes. Oh, this is very useful for text processing, and it is suited for discrete features where the column resembles some counter. So when using text processing techniques or text pre-processing techniques, we convert the text into counter of particular vocab, right? You convert the counter to particular vocab. Okay, so we'll use some pre-process technique to convert the text into okay, a text would be something like this. We'll be converting the text into words. Sorry. Start from multinomial naive Bayes. Okay. Okay, let's start with the next element, next entity, that is multinomial naive Bayes. So what we'll do over here, it's multinomial naive Bayes is suited for data which is counters. So of course it is not suited for negative numbers, right? Suited for data, the feature should be counters. and that is what generally your text processing would be. You will be converting your text data into counters, right? If you are using count vectorizers, or if you are using TF-IDF, then it would be some probability, right? Some importance of it in the scale of 0 and 1. Multinomial name base works pretty well with that. So we'll use some, so this is your reviews.csv. This is a review file, okay, and this consists of quite a large data. You can see here 5,68,000. Okay, and this is how the text looks like. Okay, this is the text value, this is a summary, and this is the score. What we want to do is we want to convert this data into positive sentiment and negative sentiment, and based on the text we want to calculate positive sentiment or negative sentiment. Of course, these are the two columns that is of our interest. One is text and one is score. These are, okay, one is text and one is score. Okay, and we are eliminating all the data which is of neutral class. Doesn't make a lot of sense. That's neutral reviews. Okay, that's what we're doing here. Next thing is if the rating is between, score is between 0, 1, and 2, we say that belongs to class negative sentiment, and if it's 4 or 5, it belongs to positive sentiment. That's what we are doing over here. Okay, rest of the columns we might not need. So this is all we need: the text and the sentiment. Okay, and if you can see here, the data is pretty much this is a sentiment distribution. One is 44377, and it's like 22, like heavily 20 80%, right? Imbalanced data. So might have to use all those techniques. The first thing would be to remove all the non-alphabetical data from it. So we are using, from analytical library, we are using a regular expression tokenizer. It will tokenize the text as well as it will remove all those non-character data like numbers, like punctuations, everything. It will get rid of that. Okay, so that's what we are doing it here. We're tokenizing the text, and this is how our text looks like. Once we are done with this, okay, we want to do stemming. Stemming again using NLTK. NLTK is natural language toolkit, okay, for dealing with text data. So we want to get the base of the word, okay, and whenever you're working with larger data sets, make sure you take subset of it, not all the data. Otherwise, your each independent step might take a lot of time in processing, and if there is a failure, you'll end up wasting a lot of time. So always take a subset of it. Do entire processing, then you can run on entire data. Okay, so the first thing is snowball stemmer. This is one of the stemming technique. It will get to the root of the word. Okay, like warming, it will return warm. Okay, so let's see. We are stemming all the words in the list, right? And we are converting it. So after we do this, and we're joining it back, right? So all the main words are only there, right? It does not consist of running separately. Only run will be there. This is what will happen here. Okay, after stemming. As we are done with this, we want to now convert the entire data into count, like words representing each column, and the value will be count, right? That's what we are using, count vectorizer. And the stop words is English, so that it gets rid of the not so important words. That's what stop word will do. And if you mention it English here, it means some predefined set of words it will get rid of. Okay, then you will be converting your data into, transforming your data using this count vectorizer here. That's what we see, review data TF. It consists of subset of the text, right? And it has converted the entire data into numbers. Each column represents some word, and the counter corresponding value corresponding to would be number of times that word appeared. Okay. Followed by that, we should be splitting our data into training and test so that we can validate our model. Okay, and again we see the class is balanced. We can, if you want, we can configure using multinomial in NB. This is the class prior parameter. We are configuring, telling it upfront. This will be the class distribution. So plan the penalty accordingly. Okay, once we train the model, okay, and we are doing the prediction. Okay, using predict, and this is the test data, and we want to see how accurate is our model. So this is on a smaller data. So you can see here confusion matrix is there. This is the matrices function that we are using to understand the class, and it's really important to understand this. So this is class 0, this is class 1, this is true, and this is prediction. So this diagonal values are the things which was correctly predicted. This is falsely predicted, and you can see data which is of class 0 but falsely predicted as class 1. data which is of class 1 but falsely predicted as class 0. Okay, that's the information confusion matrix gives you here. Okay, so of course you can further fine tune it by adding, data sampling techniques like undersampling or oversampling, smooth, right? We'll see that in later part of the course. Let's come to the third part of it. This is Burnolis naive Bayes. Like multinomial naive Bayes, which is suited for discrete data, Burnolis naive Bayes, which should be suited for binary data. Like, the column should be having binary information of zeros and ones. And if the column does not contain data in binary information, the data will be binarized. Okay, by default, we'll see that in this example. It can deal with negative numbers because whatever number is it, it can convert it into a scale of, in the 0 or 1 based on whatever you decide at the middle value. We are generating some data over here, and as you can see, the data generated is in the range of -3 to +4 along all the directions. Okay, and we are plotting it over here. Okay, we are choosing Bernoulli's naive Bayes, and we can see binarizer is 0. That means less than 0 it will be 1, less than 0 it will be 0, and higher than 0 it will be 1. Okay. Okay, once we have done this, we are training the model. Okay, and we want to see how the distribution really works. And using this technique, you can check the code here. Using this technique, what we are doing, we are generating all the data in throughout the space, and this is the data, and we are predicting the class to which it will belong. So we can see the data is actually divided into 2 classes, right? This belongs to class 0, class 1, and we can see the accuracy and all that. So what is Bernoulli's naive Bayes doing here? Based on, whatever data you are pushing, it converts into 0 and 1, and it is creating a separator over here. It's absolute 0, isn't it? Okay, so this is Bernoulli's naive Bayes. Remember, it is suited when the data is binary in number, right? Feature data is binary, 0 or 1. And if it's not, it will convert that into binary. As of now, whatever we have seen, it's all the data has to be in the RAM. And remember, in our previous example, I couldn't really run it with all the data with 5 lakh, 5.5 lakh rows. It would hog my system, or it will not be possible to bring all the data to the RAM. Okay, so what is the other way to do this out of code training, or for the data which is larger than your RAM can fit in, is as you have seen earlier in linear regression or the regression chapter, we have partial fit. So partial fit is supported in naive Bayes. Okay, so the first thing that we do is, okay, we are creating the tokenizer, we are creating the stemmer, right? We are creating instance of tokenizer and stemmer. We are and count vectorizer or TF-IDF won't work in this out of code training model because they need to maintain the state. Okay, so you need something which does not maintain state, like whatever data you give, it will transform it into a lesser dimension, or for text data, it will convert that into numbers. Okay, without maintaining a state. So hashing vectorizer is one such technique. It does not maintain state, so it's suited for higher dimension of data. So the same data again that we are using. Okay, so first thing, we are loading the file, and we are loading in read.cs. We are passing chunk size. That means it will return an iterator of size 20,000 rows every day. Okay, and we're loading from the data set. We are choosing some 10,000 random samples, and we're creating a test data out of this. Okay, these are the steps: removing all the data which is free class, converting into sentiment, tokenizing the text, stemming the words, joining it back, doing the transformation, vector transformation using hashing vectorizer. These are the default values as well. Okay, so once you are done with this, we are running it for the entire data. And remember, once I loop through it, every time it will get data of 20,000. Okay, and I have this test data. So for the 20,000 rows, I'm doing all this stuff. Okay, training the model and predicting with the data which I extracted earlier, 10,000. So as you can see, as the model progresses, the same model, you have a partial fit function. Okay, that means once the model is trained, you pass more data, it will further train the model, right? You pass more data, it will further train the model, and we should see the model improving. So without doing a lot of stuff, we can see here, first time this was the misclassification number. I'm treating the confusion matrix here. This is the misclassification, and next time it improves. It improves. So with just 20 iterations, I could see a good change in the number of misclassification. So you can further continue training the model using this data, or you can use sampling techniques to generate more data and train the model further, and you can see a better result coming out of this. Okay, that's all from Nebase. Thank you.